Okay, so I welcome you all to the next problem solving session of fundamentals of food process engineering. So here we'll be discussing the week 7 syllabus and solving problems related to that. Question 1. Which of the following statements are incorrect? A. Freezing involves the removal of both sensible heat and latent heat. B. Freezing of pure water exhibits sharp transitions between the different freezing periods. C. During the pre-cooling period, the temperature of water decreases to the freezing point as latent heat is removed. D. During nucleation, the freezing point increases to 0 degrees Celsius. So the answer is that if you look at this is the freezing curve where x-axis is the time and y-axis is the temperature. So A corresponds to that of water and B panel corresponds to that of your food product. So here you can see your A to B is your pre-cooling where you can see a decrease in temperature. So A to B is when your food product will be at a certain temperature and you need to bring it down to your freezing point. So in this case, you see that there is a reduction in temperature which indicates that you are dealing with sensible heat removal here. So at B, from S to B, you can see a slight increase in the temperature. This is because from A to this point, you can see that the temperature is reduced to the freezing point. So this is where your crystals will start forming. So the moment crystals start forming, there is a phase transition involved. So you have both sensible heat and phase transition involved in freezing. So your A option is correct. So when your crystals start forming, there is latent heat of fusion being released to induce your phase transition. So since latent heat of fusion is released, you will have because of the heat removal, you will have a slight increase in the temperature, and this is denoted from S to B here. And after your crystals begin, it will start growing more. That is, more and more water product will start crystallizing. And as you can see, this B to C will majorly involve your phase transition. That is, from water, uh, your frozen water to your ice crystals will start forming from B to C. And from C to D again, once the entire crystals are formed, now these crystals will come down to the temperature of your freezer. So your freezer will be somewhere at around minus 30 degrees Celsius, and let's say your food product is somewhere close to minus 4 degrees Celsius or so. So from minus 4 to minus 30, the frozen food product reduces its temperature. So C to D also involves your sensible heat removal. So as you can see here, your freezing will involve both sensible heat as well as latent heat of fusion removal, and hence statement A is correct. So when you compare A and panel B, you can see that A, which corresponds to that of pure water, is much more sharper, whereas in case of B, you can see multiple transitions, or it is actually in fact much more smoother in case of a food product. So so B is also correct. So why it is much more smoother in case of food product? Because the major difference you can see from B to C. Although A to B, both of them involve your sensible heat removal, from B to C, the temperature is pretty constant because you're dealing with pure water here. Whereas from B to C, you can also see a you can also see a gradual decrease in your freezing point. This is because after freezing, during freezing, what will happen is that your water crystals will start forming, and it is only the water that is getting crystallized. Your solute will not get crystallized at this stage. So the water is crystallized and removed, and your free water available in the food product reduces. And since the free water reduces, your concentration of your solute will increase in this stage. And because of the concentration solute increase, you will have something called as the freezing point depression. That is, freezing point of a solution directly depends upon the concentration of a solute. So more the concentration of the solute, more lower will be your freezing point. So during freezing of a food product, your water molecules will be frozen and your concentration of your solute will gradually start increasing. Because of that, your freezing point will also start decreasing. So that is why you can see a gradual decrease from B to C as well, but this is not seen in case of pure water since you do not have any solute in that case. So your B option is also correct. In case of C, the pre-cooling period, the temperature of the water decreases as latent heat is removed. So, but this is not the case because in A to B, you are only seeing a temperature reduction. You do not see any phase change involved. So, there is no latent heat of removal. Latent heat of removal is only happening from S to B and not from A to B. So, in the pre-cooling period, it is the sensible heat that is being removed and not the latent heat. So, our C option is wrong. And in case of D, during nucleation, the freezing point increases to 0 degrees. This is because your latent heat of fusion is now being released because you have a phase transition. And because of the release of latent heat, you will actually see an increase in the freezing point to 0 degrees Celsius. So D option is also correct. So the answer to this question is option C. Option C is incorrect because sensible heat is removed and not latent heat. Moving on to the next question. In case of a blast freezing, A. Liquid refrigerant is used, B. Plate heat exchanger is used, C. Cold air is used, and D. Concentric tube heat exchanger is used. So in this case, what happens in a blast freezing is that you have a huge chamber in which you are storing, in which your product is present, and this product will be directly in contact with the cold air. So let's say this is your blast freezer where all your products will be placed in either trays or it will be placed in a conveyor belt. So it can happen in a both batch and a continuous mode. So your product will be placed and you will have cold air circulating in the room. So this cold air can be circulated either by natural convection or it can be forced circulated with the help of a fan or so. So the outer walls of your freezer will have your refrigerant being passed. So this refrigerant will cool down the air inside the room and this cold air will come in contact with your food product and hence it is a direct contact kind of freezing technique. So it is the cold air that is used, liquid refrigerant is used outside of the freezer to cool down the air that is inside. So you will have both batch and continuous mode. But in case of batch, you will just have trays and you just have to keep the product inside. Whereas in case of a continuous mode, you will have your food product placed on the conveyor belt and based on your freezing requirements, your residence time inside your air blast freezer will vary. So it is the cold air that comes and freezes the product and hence your answer to this question is option C. Moving on to the next question. During the primary drying phase in freeze drying, what is necessary to calculate the amount of heat required? A. Latent heat of vaporization, B. Latent heat of sublimation, C. Enthalpy of water vapor, and D. Specific heat of the product. So, what is the difference between freeze drying and freezing in this case? So, freeze drying is actually where you keep a completely frozen product and expose it to very low temperatures and very low pressures and you then subject it to heat. That is, you have air coming in that will remove the heat from the product. So in this case of freeze drying, what happens is from the frozen product which has ice crystals and everything, that ice will directly sublime into gas. So instead of going through from ice to liquid to gas, it will directly sublime from ice to gas and hence it is called as freeze drying. So first you'll freeze the product and then you'll dry the product without having an intermediate liquid phase at all. So that is the difference between freeze drying and freezing. So in case of freeze drying, you're actually removing the moisture content through sublimation. Whereas in case of freezing, you will have only your water molecules being frozen. That is, your water molecules are immobilized for preservation. Whereas in case of freeze drying, you're removing the water moisture content to enable preservation. So that is the difference between freeze drying and freezing. So in freeze drying, you have multiple phases involved. So one is the primary phase where your frozen product will have free ice on the surface of it. So the sublimation of this free ice into your vapor is primarily involves your primary drying phase. So at this stage, your pressure is lowered and your temperature is also lowered, and the latent heat of sublimation is provided to enable your primary drying. Hence, we use latent heat of sublimation to calculate the amount of heat required for a primary drying phase. So, what is secondary drying phase? Secondary drying phase is the removal of water molecules that are bound to the product. So, the major difference between primary drying phase and secondary drying phase is that primary drying phase need to happen at a very low temperature. This is required in order to prevent the ice from turning into liquid. So, the moment your ice turns into liquid, it is no longer a freeze drying. You will have to include evaporation as your procedure to remove the water. So, here in freeze drying, sublimation is the process that is happening. Hence, you need to make sure that your ice is always frozen and always in solid state instead of it melting into liquid. So, your primary drying phase always occurs at a very low temperature. Whereas in case of secondary drying phase, already majority of your free ice is already sublime, and what you have left out is very residual amount of water molecules that are bound to the product. So in this case, you need not worry about the risk of turning ice to liquid. So your secondary drying phase can actually happen at a slightly higher temperature than that of your primary drying phase. So secondary drying phase in fact starts towards the end of your primary drying phase itself, where your free ice starts to completely sublime. So latent heat of sublimation is what is used for calculating the amount of heat required in freeze drying. Latent heat of vaporization is involved in evaporation process, where you are dealing with liquid water to vapor phase. And enthalpy of water vapor and specific heat of the product is also involved when you're dealing with sensible heat and you're dealing with evaporation in this case. In this case of freeze drying, you already make sure that your product is completely frozen for faster freezing processes, and hence you need not require specific heat of product and enthalpy of the water vapor much. So the answer to this question is option B. I hope this is clear. So moving on to question 4. At what point ice crystal formation takes place during freezing process? A. Below the material's freezing point, B. Below the material's triple point, C. Below the material's dew point, and D. Just above the material's triple point. So you need to understand what is the difference between all these three temperatures. One is the freezing point, B the triple point, and C the dew point. So freezing point is the temperature at which your phase transition will freezing point is the temperature at which you will start your ice starts to your liquid starts to freeze into ice. So that is your freezing point. So how it is different from triple point is that here when you see the graph, triple point is this black dot that is given here. So this triple point is the temperature and the pressure, corresponding pressure at which all the three states, that is your solid, liquid and gas, can coexist. So above this triple point, you will only see either of the two phases. You cannot see all the three phases. So above the material's triple point, you will have either liquid and the gas, which is not what we require for freezing process. And below the triple point is when you will start seeing a lot of solid and less of gas. So below the triple point and at certain, let's say at 1 atmospheric pressure itself, you can see it is entirely solid. And you can also see that your triple point is slightly higher than that of your freezing point. So at triple point itself, you will start to see your ice crystal formation. And this ice crystal formation will grow more as you further decrease the temperature to your freezing point. So that is actually the supercooling that is seen in the freezing curve, if you can look at it. So TF is where your crystals will start growing, whereas your nucleation or your point at which your ice crystal formation takes place is at triple point. That is, that any temperature below your triple point is where your liquid can no longer exist, and it is only the ice crystals or solid that exist. So the answer to this question is option B. So you need to know the difference between freezing point and triple point. Freezing point is actually a little below than your triple point, and actually when you start reducing the temperature below triple point itself, you will start to see your solid coming, that is your ice. So you need not actually go till the freezing point to start the ice crystal formation, but freezing point is required to grow the ice crystals, that is to increase the amount of ice crystals. So what is dew point is that dew point we discussed in the humidity chapter. The dew point is the temperature at which your water vapor will start condensing into liquid. So that is involved in humidification process and not in the freezing process. So that is how dew point is different from freezing and triple point. The answer to this question is option B. So question 5 will move on to numerical. In an air blast freezer operating at minus 30 degrees Celsius, blocks of fish of 0.0508 meter thickness are to be frozen. The initial temperature of the fish is minus 2.2 degrees Celsius and the moisture content is 82%. The heat transfer coefficient of the freezer is 20 watt per meter square Kelvin. Calculate the freezing time in hours and assume the density of the unfrozen fish as 1050 kg per meter cube. The thermal conductivity of the fish as 1.025 watt per meter Kelvin. The latent heat of fusion is 335 kilojoule per kg and the shape factor is P equal to 1 by 2 and R equal to 1 by 8 for an infinite slab. So we have two equations to determine the freezing time. One is the Planck's equation that does not involve sensible heat. The other is your Fam's equation. So here there is no mention of decreasing the temperature of a fish from your ambient temperature to the freezing point. Here the fish is already at minus 2.2 degrees Celsius. So you're actually starting the freezing time calculation from B. That is, in the freezing curve, you have already frozen the fish. That is, you've already reduced the temperature to the freezing point, and that is when you're calculating the freezing time. So you're not including the sensible heat in this case. So when you're not including the sensible heat removal, you use something called as a Planck's equation. So we'll first move on to what is given in the question. So you're considering an infinite slab where your heat removal happens only through one direction. The rest of the two directions are infinite in length, and A is the only thickness that you can measure. So in this diagram, A will be your thickness of your fish, TF will be the temperature at which your fish is present, that is the slab surface, and TA will be the temperature of your freezer, that is the outside air temperature will be TA. So given TA is equal to minus 30 degrees Celsius, A is equal to 0.0508 meters, which is your fish thickness. TF is minus 2.2 degrees Celsius. W, which is your moisture content, is 0.82. You have H, which is your convective heat transfer coefficient, as 20 watt per meter square Kelvin. Density is 1050 kg per meter cube. You have thermal conductivity as well, which is K equal to 1.025 watt per meter Kelvin. The latent heat of fusion is given as 335 kilojoule per kg. P is half and R is 1 by 8. So why we have two different heat transfer coefficient? One is convective and one is conductive because your outside of your slab surface is exposed to air. So that is cold air. So your heat removal will from the surface will happen via convection. So whatever heat from the surface slab to your surrounding air will be heat convection. But you need to freeze the sample till the middle of the fish slab. So your heat has to transfer all the way till the inside of your slab. So this inside of the slab, since it's a solid, we deal with conduction. So from the middle of the slab to the surface of the slab, you involve conduction, and from the surface of the slab to the surrounding air, you involve convection, which is why you have both H and K involved in this particular problem. The freezing time according to Planck's equation can be calculated as TF, which is the freezing time, is equal to rho L divided by TF minus TA into PA by H plus RA square by K. So rho is the density of the unfrozen food product. L is the latent heat of fusion of your water molecules or your moisture content. Since it is the moisture content that is being crystallized, you need to deal with the latent heat of fusion of that moisture content. TF is your slab surface temperature. TA is the temperature of your freezer. P and R are your shape factors which depend upon the kind of geometry that you are dealing with. A is your slab thickness. H is your convective heat transfer coefficient and K is your conductive heat transfer coefficient. So what you need to first figure out is that what is given is your latent heat of fusion in the for the entire product. But since it is the water molecules that crystallizes first, we need to deal with the latent heat of fusion of the water molecules and not for the entire product, including the solute and all. So L is equal to lambda into W. So where lambda stands for a latent heat of fusion given in the question and W stands for the moisture content. So from these parameters that is given in the question, your lambda is 335 kilojoule per kg and your moisture content is 0.82. So your total latent heat of fusion of the water molecules that you are dealing with in the freezing process is 274.7 kilojoule per kg. So you need to make sure that you're including the latent heat of fusion of the water molecules and not of the entire product in case the moisture content is given in the question. So substituting the freezing time formula, TF is equal to rho L TF minus TA into PA by H plus RA square by K. So when you substitute density as 1050 kg per meter cube, L is your 274.7 kilojoule per kg that we calculated in the previous step, and we are converting kilojoules into joules, so we are multiplying it into 1000. And TF is your slab temperature, which is minus 2.2. TA is your freezer temperature, which is minus 30. and P and R are 1 by 2 and 1 by 8. The A is the thickness of the slab given as 0.0508 meters. H is 20 watt per meter square Kelvin and K is 1.2025 watt per meter Kelvin. So when you find out, when you calculate TF in hours comes out as 4.57 hours. So I hope this is clear. You need to, this is the main part where when you have moisture content, you need to calculate the rated heat of fusion of the moisture content. And then if sensible heat data is not given, you can assume Planck's equation to calculate that freezing time. So the answer to this question is option A. So moving on to question 6. Dash are formed when crystallization takes place for a very long time. So A, no crystals, B, small crystals, C, large crystals, D, none of the above. So what happens during a crystallization procedure is that I'll give you a summary of what I've written here. So in a freezing process, as your ice crystals are formed, the amount of free water that is present in your space between the cells. So between the cells, whatever space is there, that is where your crystal formation will start because there is water there. So your water will start crystallizing and the amount of free water present will reduce. So since your amount of free water reduces, their solute concentration increases in the intercellular space. So when you compare the inside of the cell and outside of the cell, you will actually have a concentration gradient. Outside of your cell, you will have reduction in the free water molecules, and hence you will have an increase in solute concentration. Whereas inside the cell, you will have a low solute concentration and relatively high amount of free water. So there is a concentration gradient established now. So your water molecules will start moving from inside of the cell to outside of the cell. And since your water molecules will diffuse from inside to outside of the cell, you will have more water as your crystallization proceeds or as your freezing proceeds. You will have more amount of water molecules available in the intercellular space because of diffusion. And because more water molecules are available, you will have more crystals forming and larger crystals forming. So more and more crystals are forming, they tend to coalesce and become a large crystal. So water diffusion from inside to outside of the cell will increase the water availability, resulting in crystal formation coalescent. So in case of a slow freezing, you will have enough time for this diffusion to take place. So when you are freezing the product very slowly, your water molecules will have enough time to come out of the cell and will have enough time to form crystals, grow and then coalesce. So in case of a slow freezing, you will have large crystal formation, and these large crystal formation will then puncture the cell membranes, and this puncturing of the cell membranes will cause damage, and then it will result in leakage of the cell contents and also the loss of food quality. So when you thaw these food products that are subjected to slow freezing, you will actually have loss in food texture, nutrients, as well as you will have a very dripping kind of a food product. Whereas in case of a fast freezing process, you're just rapidly reducing the temperature and freezing the product. So your water molecules will not have enough time to come out of the cell much and then help and then result in growing and coalescing of the crystals. You will still have crystals, but they'll be very tiny, and they will not rupture or damage your cells in the food product. So which is why slow freezing is not much preferred, because it can damage your food products, and hence you can say that your slow freezing results in large crystals during crystallization or freezing process. So your answer to this question is option B, which is option C, which is large crystals. So yeah, large crystals are formed when you have a long crystallization time. Statement 1, the freezer burn results in irreversible changes in the color, texture, flavor and nutritive values of the food. And statement 2, the freezer burn takes place in unpackaged food in air blast freezers. So as one of you had mentioned, the answer, both of this is true. So what freezer burn is that, as you keep the food inside the freezer for a very long time, there's moisture loss from the food. So basically, since your water is now getting removed because of long time freezing and poorly packed food, that is the main part of it. So, for a poorly packed food which is exposed to your directly exposed to your cold air, what happens is there's a moisture loss, and because of the moisture loss, your food gets dehydrated and gets especially the meat and all starts shriveling up. So because of this shriveling up and loss of moisture, the oxygen now starts taking the place of water inside your food. So because now your product is not fully properly packed, your product will not only be exposed to the cold air, it will also be exposed to oxygen. And because of exposure to oxygen, you will actually see oxidation reaction taking place that will result in loss of pigmentation. It will harden up your food product, and it will cause a very dry and grainy brownish kind of area as seen here. So these brownish area are actually the freezer burn that happens. Your food is still edible, it is still usable, but then the quality of the product is irreversibly damaged. So your statement 1 is true. And statement 2 happens, this is in unpackaged food in air blast freezers. So for this process to take place, first thing you need direct contact with air that happens in air blast freezers. And second thing, this happens only when you have poorly packed food. So in this case, in case of air blast freezers, if you had a properly packed food, you could actually reduce this freezer burn phenomena. So freezer burn actually takes place in unpackaged food in air blast freezers mainly. So the statement 2 is also true. So the answer to this question is option D. Is this clear? So we'll move on to the next question. Question 8. Planck's equation is used to estimate the convective heat transfer coefficient in a food being frozen between the refrigerated plates with the plate temperature of minus 30 degrees Celsius. It took 23 minutes to freeze the product. The following data are available. Freezing temperature is minus 2 degrees Celsius. The latent heat of fusion is 280 kilojoule per kg. Slab thickness is 20 millimeter. Density of the food is 880 kg per meter cube. Thermal conductivity is 1.5 watt per meter Kelvin, and the initial temperature of the food is minus 2 degrees Celsius. So the fact that initial temperature of the food and your freezing temperature is same indicates that you already have a food at the freezing point, which means you need not reduce the temperature further in terms of sensible heating. So since your product is already at freezing temperature, any more reduction will actually cause only a phase transition and not sensible heat. So this you need to take care. Since the initial temperature of the food is same as the freezing temperature of the food, you need not require sensible heat removal at all. You only need latent heat of sublimation in this case, latent heat of fusion in this case. So we are using Planck's equation, which ignores sensible heat. So again, this is same exactly the same formula as we used in the previous questions. So TF is equal to rho L divided by TF minus TA into PA by H plus RA square by K. So in this case, like the previous question, you do not have the moisture content here. So we assume that whatever latent heat of fusion given is actually the latent heat of fusion of the water molecules in the food product. So you can just directly assume if you do not have any information regarding the moisture content of the food. So when you substitute the values, you get for an infinite slab, for an infinite slab and for an infinite plate, your P is equal to half and R is equal to 1 by 8. Whereas in case of an infinite cylinder and a sphere, you will have different P and R's that is discussed in the lecture videos. So for an infinite plate, P is equal to half and R is equal to 1 by 8. So we are substituting the values here. It is given 23 minutes. So we are converting it into seconds. That is 23 into 60. 880 kg per meter cube is your density. 280 is the latent heat of fusion. Since you do not have any data regarding the moisture content, we are directly substituting it. 280 and we're converting it into joules. So 280 into 1000. Minus 2 degrees is your TA, which is TF, which is your temperature of your slab. Minus 30 is your TA, which is the temperature of your freezer. So half into 0.02, which is the thickness of your slab, divided by H, that is what we need to figure out. That is Planck's equation will be used in this case to figure out the heat transfer coefficient, convective heat transfer coefficient. And R is 1 by 8 and A is 0.02 whole square divided by 1.5, which is your K. So when you simplify this down, you will have 1380 equal to 88 into 10 power 5 into 0.01 by H plus 3.334 into 10 power minus 5. So H is coming out to be 80.98 watt per meter square Kelvin. Is this clear? Any doubt? The answer to this question is option D. If you want me to repeat also, we can repeat. So this is the Planck's equation. Moving on to question 9. What are the limitations of the Planck's equation for freezing time calculation? A. The density values of the frozen foods are difficult to measure. B. Does not account for sensible heat changes. C. Constant thermal conductivity is assumed. And D. All of the above. Any clue what the answer is? So both the numerical sums that we discussed were based on Planck's equation only. So what we assumed was the density of the frozen fluids are difficult to measure. So once you have frozen the fluids, you will have some crystallization effect. You will have some of the water molecules that are being removed as well. Also, although that is not very significant in terms of freezing, sometimes when you freeze it for a very long time, you will have a loss of moisture as well. So the density of the frozen fluid is actually difficult to measure because your composition might slightly vary after freezing. So even in the question, if you had noticed, we are assuming the density of the unfrozen food and not of the frozen food. So we do not know after freezing what is the density of the frozen fluids. So Planck's equation assumes only the density of the frozen fluids. So A is correct. And B, all this while we were mentioning that we do not assume the sensible heat changes at all. So if you look at the freezing curve as we saw in the first slide, so A to B, and after F is your sensible cooling that is happening. A to B is when your product is cooled down to its below its freezing point. This involves the temperature difference, hence sensible heat. And after F, that is your completely crystallized and frozen food, is now brought to the temperature of the freezer. So below F also you are seeing a drastic temperature change and hence involves sensible heat. In case of Planck's equation, we are considering this as your TF, that is after your crystallization has begun and then till the end of your complete crystallization, including the solute crystallization, is what you're considering it as freezing time. So all the sensible heat loss you are not considering during Planck's equation. So this is your TF in case of a Planck's equation, and hence it does not account for sensible heat changes. And again, thermal conductivity is also assumed constant. So in both the problems that you notice, we have only one thermal conductivity value mentioned. But you can see that you are freezing the freezing the product, so you're decreasing the temperature as well. So thermal conductivities are all properties of solids that depend upon temperature a lot. So actually thermal conductivity will vary during the entire freezing time and will not remain constant. But for simplicity purposes, Planck's equation assumes a constant thermal conductivity of the frozen region. So hence um, all the three assumptions are true in case of Planck's equation. Hence the answer is option D. So any question? In case of a FAM's equation, it will include both A to B and after F as well. So the freezing time will be the entire time mentioned here. In case of Planck's equation, you will have only this region being taken as the time of freezing. Moving on to the next question. Match the following. A. Cryogenic freezing. These are all different types of freezing and freezers. A is cryogenic freezing. B. Individual quick freezing. C is plate type freezer. And D is scraped surface freezer. And for one is fluidized bed freezing, conduction heat transfer, raw material in the form of slurry, and liquid nitrogen and carbon dioxide. So which do you think is the answer? So what is cryogenic freezing? Yeah, A is 4 because you are dealing liquid nitrogen and carbon dioxide are the refrigerants used for cryogenic freezing. So that narrows down to either option A and option B. So what is individual quick freezing? B is no, individual quick freezing is not that. So what is individual quick freezing is that you are freezing each and every particle, of each and every food product is exposed to your air or is exposed to your cooling fluid. So individual quick freezing is actually fluidized bed freezing. So in a fluidized bed freezing, you will have a perforated conveyor belt sort of a setup where the belts will have holes in it and your product will be placed on top of the conveyor belt. So when air is supplied from the bottom, because of these perforated holes in the conveyor belt, your food product is now slightly start to rise. That is, it will act like a fluid on top of the conveyor belt. It won't actually be stationary in the conveyor belt. It will constantly be disturbed by the air. So when you deal with very small food products and very small food particle size, you will have something called a fluidized bed freezing where all the sides of each and every particle will be exposed to your air. So the diagram of this is given in one of the lecture videos as well. So in case of fluidized bed freezing, each and every particle on the conveyor belt will be exposed to air because of the perforation, and this results in extremely quick freezing from all the sides. So B is actually fluidized bed freezing. So plate type freezer is what happens when you have deal with conduction heat transfer. In a plate type freezer, as we saw in the numerical before, your food product will be placed between two of your plate or either one side of the plate. So you will have heat removal either from both the sides of your food product or one side of your food product. But since we are dealing with plates here, first your heat removal has to happen from the surface and onto the plate and then outside of the plate. So your plate will act as a metal or a surface contact through which your heat removal is happening. And since plate is a solid, you are actually dealing with conduction in this case. So from the surface of your food product, heat will be transferred onto the plate, and from the plate, heat will be transferred to the surrounding air or the refrigerant that is supplied. So plate type freezer will fall under conduction heat transfer. In case of scraped surface freezer, you are actually sending in the raw material in the form of a slurry. So this happens very much in case of ice creams also. So you'll have a very slurry kind of a material that will pass through your freezer. Sorry, just a minute. Yeah. So you'll have your your ice cream being passed into the freezer, and you'll have the outside of your freezer being circulated with the refrigerant. So that will cool down the ice cream, and then you will have something called an agitator as well that will have a scraper also, scraper blades as well. So what will happen is, as your ice cream or your food product starts to freeze, it will stick onto the wall, so you will kind of scrape it out and then remove the crystals or the frozen product. So this dealing with scraped surface freezers are generally used in case of ice creams where you need to scrape out the frozen food after it is freezed because of the refrigerant. So for D is your 3, that is the raw materials are supplied in the form of a slurry, and C is 2, B is 1, and A is 4. So the answer to this question is option B. So that's all for the lectures. If you have any doubt, you can let me know.